welcome everyone. Thank you for coming. Um, Big crowd, honestly. Did not expect that. But thank you all. I guess AI is maybe interesting, but we'll see. So yeah, let's start off. Who am I? My name is Oliver Back. I'm the head of hacking at Hadrian Security. Also a yeah. Kan you harder? Okay, yeah, like the time that we're supposed to start is now, so I'm like not sure if I should wait for the sound to go down. Um, but yeah, it's a bit like I don't think it's going to be less loud yeah. It's not going to be less loud, right? No, it's just so. Sorry, but this is going to be it. Um, so yeah, I'm the co-founder of Hadrian Security. I'm also the head of hacking. I've been hacking since I'm about 11, 12 years old. Started doing bug bounties. I don't know if anyone here is familiar with that, but I've been about 11 years in HackerOne, and before that I did a lot of responsible disclosures, slash coordinated vulnerability disclosure to Dutch banks and other instances, which was fun, but security has developed quite a lot over the years. And I also became a HackerOne elite. So this is something they give to the HackerOne hackers, if you're familiar with them, once every year. It's a group of 2-3 hackers maximum. So it was quite a fun achievement to give you a poster with it. So yeah, that's a bit about me. So I work for Hadrian Security, and what we're trying to do is to build an autonomous hacker. And that basically means that we're trying to reproduce what a hacker would do, but automate it in a way that we don't have to do as much manual work as normally required. This can be quite challenging, but AI is actually allowing us to do a couple of things that previously we wouldn't be able to automate because it just required too much guessing and then regexing, and then it's just basically impossible to automate before. So applying AI can be applied to a lot, which is not very much our main interest. We're not trying to build like a Pandora's box of a hacker, like one single model that approaches the entire problem at once. We're looking into automating small steps, and it can be applied to multiple facets in that way. So to give you an example, when you're looking at an organization from the outside, reconnaissance and contextualization is very important. You need to understand what you're actually looking at. Something else that we do is like we hack using a tool called Burp. I don't know if anyone here is familiar with that, but it basically allows us to generate hints of things that you could potentially look at next. And we also do automated exploit development and mass exploitation using AI. And I'll show an example of mass exploitation and some other stuff soon. So recon and contextualization or reconnaissance. When I'm hacking, 95% of my time, I would say, I'm not actually trying to hack something, right? I'm trying to find something that I can hack. So you really like just looking around, trying to figure out like, is this something that's interesting to spend time on and poking at? And this can be very tedious. But basically what you're trying to do is trying to understand the target. Like, what am I looking at? How does it function? What am I actually hacking? So we've built a couple of tools here that are, I think, quite interesting. So the first tool that we've built is is an AI model that can predict the age of a website. So for example, you provided a URL, and it's going to be able to predict like this website is built somewhere in the year 2014. We don't do this based on the way the website looks, but we do it based on the underlying technologies. So for example, an outdated JavaScript version that has been released in 2011 might indicate something, and a copyright banner might indicate something, but it's really much about the entire package that you're looking at, which can help you to predict the age of a website. And this is important because if you look at older websites, they're more often more vulnerable. Something that's legacy very often also has legacy type of vulnerabilities and hasn't been maintained for a longer time. So for us, this is something very interesting to look at. And the second one is classification. So what kind of web page are we actually looking at? Is it a web shop? Is it an administration panel? Is it something that's in production? Is it an API? Is it staging? These kind of things matter because it helps you to correlate back to what you're actually looking at. Because, for example, if you're looking at a web shop, you'll try different attacks that you would normally try than if it's a API. Like if you, for example, discover that you're looking at a web shop, it might be interesting to classify all the forms you see on that website, and then look where the Add to Cart button is. And when you find the Add to Cart button, you might try to add a negative amount of numbers to see if you can, for example, order a minus 10 items. And then when you go to the checkout page and the total price is minus 10 times the price, then there's a flaw there. But being able to do this just by scripting is incredibly difficult. But with AI, being able to classify what you're looking at and look at each form and each page, you can actually build a chain of, hey, it's a web shop, you can order a negative amount of numbers, and you can see it here at the checkout page. These kind of vulnerabilities are more logical, but they're very helpful. It's very helpful to use AI to exploit these kind of vulnerabilities. So to give a quick example of the model that we've built, let's see, is this one, is this big enough? Yeah. So I'll run it live. So I have a list of URLs here. As you can see, like it's our own website, it's a web shop, it's some other stuff. It's just a random list of websites. And then we can run our prediction model. We mainly build these things in Python because Python is just the way that you build AI models. There's not much there that really helps with, mainly it's all Python. So what you can see here is that we have a Chromium browser, basically a headless browser that loads these web pages and then gives all the data to our AI model. For example, you can see here that this website is classified as a web shop. We think it's from around 2019. And this website is classified as a login panel, which we also think about that date. And then we have this website, which we think is super old. So for example, if you look at this one, which is a user credential input, you can then, let's see if it opens. There you go. So very obviously it's a login panel. And then if you look at this older website from 2013, if you open that one, it is quite obvious that this is a very old website. So this is something that will be then interesting to look at and try to exploit. Mainly because it probably has not been maintained for the last 10, 20 years. So how do we actually develop exploits using AI? Well, this is part of one, training the data, then generating the exploit, then checking it for safety, and then doing manual verification, basically. So give you an example, what we do is we log all traffic that we do when we're hacking a target as the hacking team, and we then label that. So we use a tool called Burp again. We store all the entire file. We label all the requests that we've made, and we use that to help train the AI model to figure out what is correct and what is incorrect. Something else that we've done is we just scraped a lot of sources. So we're able to, for example, use open source resources on GitHub. There are books, blogs, exploits, codes available. We can use this to train models as well. And we do this for each independent vulnerability category. So again, we're not building a black box, but for example, for cross-site scriptings or SQL injections, we will build independent models to try exploitation. The reason for this is that if it becomes one big black box and you don't know what's actually happening in there, it doesn't make any sense to help advance it any further. It becomes a deep learning model then, and it becomes quite unpredictable in what it actually does, which in hacking can be quite a problem when it starts doing things it shouldn't be doing. So for example, for safety, what we do is before any command is executed, it's verified by an independent LLM. So we say like, hey, this is what we want to do. Do you think that this is something that we could execute safely? And then if it says no, we will, here's an example for a SQL injection. So we've generated an exploit for a SQL injection in a search, which you can see by the or sleep 5, which would, if it works, make the page delay for 5 seconds or 10, depending on how often the SQL query runs. And then we send those queries to an LLM. So as you can see here in the second one, the or sleep is deemed safe, the comma is deemed safe, but the drop table users will be rejected by the LLM because you don't want to drop tables. It is a good way of defense, I guess, but it's not going to be very good on the web application. And then we verify. So the LLM model is able to verify, like, okay, you made this request, this was the input, this is how long it took, and this was the output. Did it work? And that way we can verify, for example, SQL injection just purely based on data that we've trained from a model, and by making the request before that, checking if they're actually safe. So we've also made one of these tools for cross-site scriptings. It's quite a common vulnerability. It used to be more common. It's changing a lot more to like prototype pollutions or like other type of exploitations where it's the same effect, but it's not really a straight up. You put A in, it doesn't render correctly, so it's a cross-site scripting. To give an example, boom, 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 boom. Yeah. So what we're doing here is we're running a model on our API cluster, which will then authenticate and make sure that we can actually safely and legally run the model. Then we provide it with a URL. It spins up the Chromium browser, and it browses to that URL. And then it validates the response. It's okay, so it can start looking at what actually happens when you load that web page. So often JavaScript or images or style sheets in the background will make multiple requests. So you can see in the backend or the client side that more requests are being made here. And then we analyze those files. So in JavaScript, for example, you can often find a lot of parameters, or sometimes we also find like credentials or other type of stuff in these files, and we analyze that and we pull it out. So we were able to find the input fields, then we were able to find the parameters in the JavaScript, and then we look at the AST tree, which is basically the way that JavaScript executes in the browser 2 hops, to see how it actually evaluates all the user input. So if you put A in function B, what does happen here, here, and here, and how can we follow that into an output into the browser? And then it looks for all the fields, essentially, and it tries to figure out how it can exploit those. For this proof of concept, I disabled post because it takes long, but it looks at the reflection of input. So it found that the Q parameter reflects input on the front end, which you can see here. So we have an input here, and it reflects here. So now it knows that it can try to put like cross-site scripting payloads in there. So it does a couple requests. It looks at how it works. It then goes to the safety check, which is the LLM. It validates if the payload is actually safe to send to a server, and then analyzes the responses. So in this example, you see we've tried 6 payloads, and 2 of those worked. And that makes sense because if you, for example, look at this one doesn't render in the DOM. If you put a script payload in the JavaScript DOM, it won't render immediately, so you need to find a bypass for that. So if you, at the end, go to, let's see, copy this one. Right, so this one, for example, won't render. But if you take, like this one, so we'll take this one won't render, this one will. And the reason this one renders is because it's inside the DOM and you cannot load a script tag inside the DOM through JavaScript. It would just not execute. So that's the way that you can detect cross-site scripting using AI by analyzing the JavaScript, figuring out the input, reflection, and output, and then sending it to an LLM to reproduce the vulnerabilities. So we do similar things for 0 days, which often now are very quickly exploited. So previously, if a 0 day was released, it will maybe take a month, 2 months before you would actually see wide exploitation. But because it's quite easy now to very quickly scan the majority of the internet, the time to exploitation went from enough time to patch to half a day, sometimes 2 days. So we as also have to figure out a way that we can very quickly keep up with these new exploits, and AI helps with that as well. So if you look, for example, at Screen Connect, you can see that on February 19, the first proof of concept was released by an independent researcher. The 21st, there was a POC available, and already exploitation in the world started. And on the 22nd, you could see that Lockbit had already deployed their ransomware on these vulnerable instances. This is not uncommon. Like the majority of the exploits you see now that are actually classified as critical will be exploited within the first 2 days, normally the first day, depending on how difficult it is to actually figure out how the exploit is working. You saw the same with MoveIt. This was actually exploited before even the CVE was assigned. So if someone found the exploit and they already saw that it was being actively exploited in the world before they found it. And these kind of cases are difficult to protect against, but there are things that we can do. So when we see that a new zero-day drops, we monitor these from CVE feeds. We then try to extract exploits. So this can be by crawling GitHub. There's a Chinese variation of GitHub, which has a lot of sources as well. Collecting all these sources to then give it to a model to figure out if an exploit is available is something that can be done quite autonomously. So if you looked at the Cubs exploit, which is from a couple of weeks ago, we found the POC, and the first thing we did is figure out what the requirements are. So for this exploit, you needed to be able to make an outbound UDP request. You needed a callback server, and you needed an input, where the input is basically the target, which was an IPv4 address, or IPv6, but that's a very different challenge to collect those. So what we do is we set up a callback server. We generate a PR that basically triggers this exploit. And then we send a merge request to our GitHub repository. So we then manually verify if that exploit is actually correct. But that way, for new zero-day vulnerabilities, we can very easily and quickly figure out if a certain exploit can be automated, and also minimize the time it takes to actually exploit these kind of, or build a POC for these vulnerabilities, which nowadays is necessary. So we've also, I don't know if anyone here knows the Day, but I do volunteer work there. So the next thing we did was actually run a scan of the entire Netherlands and see if we could exploit this vulnerability. We found about 600 instances that were vulnerable to Cubs, but I'll be honest, I think it was a bit overhyped. I don't think it was that critical as it was perceived to be. But at least we were able to then alert all the organization in the Netherlands that they were vulnerable to Cubs, which we found 600 instances, about 300 of those were one university who got way too many IPv4 addresses. Yeah, that was my presentation. If there are any questions, please let me know. We'll also have a booth, so feel free to come by. Yeah. Thank you.